The flight controls of the A300 consist of the primary controls, which provide control about the three axes of the aircraft, and secondary controls used to change the wing's lift and drag characteristics. The associated control surfaces are hydraulically actuated with no manual reversion. The primary controls for roll are 2 all-speed ailerons, 2 low-speed ailerons, and 6 roll spoilers. For yaw control, a single rudder surface, 2 elevator surfaces, and a trimmable horizontal stabilizer is provided for pitch control. There are high lift devices on each wing. They consist of 2 trailing edge flap sections, 1 Kruger flap, and its notch flap at the wing root. Furthermore, to improve the aerodynamic characteristics, the all-speed ailerons deflect downwards when the flaps are moved to 8 degrees. The lift dumping devices on the upper surface of each wing consist of 2 inner speed brake panels and 2 outer speed brake panels. In flight, these same panels are used together as speed brakes. On the ground, the speed brakes and the roll spoilers are used simultaneously as ground spoilers. The flight controls are hydraulically actuated using the 3 hydraulic systems, blue, green, and yellow. They are completely independent, so that the loss of one hydraulic system does not affect the other 2, nor the safety of the flight. Each of the ailerons, rudder, and elevator is actuated by 3 servo controls which work simultaneously. Each of these servos is supplied by a different hydraulic system, and each servo control pilot valve is fitted with a jam detector. The horizontal stabilizer is actuated by 3 hydraulic motors which operate simultaneously. Each motor is supplied by a different hydraulic system. The pilot valve of each hydraulic motor is fitted with a jam detector. Flap actuation is achieved by a motor block that incorporates 2 hydraulic motors which operate simultaneously. Each of them is supplied by a different system. Slat actuation is achieved by a motor block of the same type as the flaps. The flaps and slats on each wing are fitted with asymmetry detectors. The slats and flap motors are supplied from each system through a priority valve. This valve cuts off their supply when the corresponding system pressure drops below 1885 psi. This maintains the primary flight control supply. In addition to the slats, the A300 is fitted with Kruger flaps and notch flaps. Each of these flaps is operated by a single actuator. The slats and flap motors, as well as the Kruger and notch flap actuators, are supplied through a priority valve. This valve, like the slats and flaps, cuts off their supply when the corresponding system pressure drops below 1885 psi. This maintains the primary control supply. An electro valve permits hydraulic fluid under pressure to flow to the primary controls and speed brakes. This valve is open when the solenoid is not electrically supplied. Each one of these electro valves are controlled by means of a selector on the servo control panel, located on the center overhead panel. When the selector is positioned to on, the corresponding electro valve solenoid is de-energized and the valve is opened. With the selector off, the electro valve solenoid closes the valve. The test position is used by maintenance personnel only, and this is important, only on the ground. The test function is not inhibited in flight. When the selector is set to this position, it has the same result as if it were set to off. The associated electro solenoid would not be powered and closes. A mechanical lock makes it impossible to set more than 2 of these selectors out of the on position at the same time. There is a pressure low magnetic indicator that displays the pressure in each system downstream of the electro valve. This magnetic indicator has two positions. Inline indicates normal pressure, while amber indicates a pressure lower than 1450 psi. In the event of an individual servo control valve jam in the ailerons, rudder, or elevator, the jam amber warning light comes on, and the servo's light illuminates on the master warning panel, accompanied by a single-stroke chime. The jam and servo's warning light go out when the selector related to the corresponding system is set to off. As we have already seen, the electro valve closes and the corresponding flight controls are not supplied by the respective hydraulic system. The pressure low magnetic indicator turns amber. Now let's go into the primary flight controls with a little more detail, starting with roll control. Roll control is provided by two identical coupled linkages and cable paths from the control wheel to the corresponding wing. The captain's yoke controls the left wing surfaces, and the first officer's yoke controls the right wing surfaces. Under normal circumstances, the yokes are coupled by a spring strut, so both move simultaneously when either yoke is rolled. Rods and cables position a cable quadrant at the differential unit. The differential unit turns a shaft. Three servo valves are connected to a shaft and are each operated by a different hydraulic system. The shaft positions the valves to cause hydraulic pressure to move all speed ailerons up or down. The differential unit also receives inputs from the pilot, autopilot, and trim control. Included in a differential unit is a spring assembly, which provides the artificial feel for roll control. When the aircraft is on the ground or in flight with the slat flap lever out of the retract position, the low-speed ailerons are connected to the all-speed ailerons by cables. So, if the all-speed ailerons are moving, then through an unlocking jack screw, the low-speed ailerons on each wing also move. When the slat flap lever is in the retract position and in flight, the jack screw, controlled by a computer, locks the low-speed ailerons to prevent that surface from moving. Controls and indicators of the low-speed aileron connecting units are grouped on the low-speed ailerons panel located on the overhead. When the magnetic indicator shows inline, the low-speed ailerons are connected. When cross-line, they are disconnected. In the event of a discrepancy between one or both connecting units and/or the slat flap control lever position, the low-speed aileron light will illuminate. It is accompanied by a configuration light on the master warning panel and a continuous horn. A switch, which is held in its auto position by a guard, can be used to override the automatic controls to either disconnect or connect the low-speed ailerons by the use of a jack screw. The computer test is for ground test only. To increase the aerodynamic efficiency of the wing at low speeds, a droop signal from the flap position causes the all-speed aileron to deflect to a maximum of 10 degrees down. This occurs when the flaps are moved to 8 degrees. The all-speed aileron linkage controls the position of the roll spoilers as well as the low-speed aileron. A full-stroke unit provides the transmission of the commands from the all-speed ailerons to the low-speed ailerons and roll spoilers. However, when the flaps are down, this same unit prevents the droop signal for the all-speed aileron from being transmitted to the low-speed ailerons. Spring units bring the spoilers or low-speed ailerons back to a neutral position in case of a failure of the control linkage. Each of the three roll spoilers is actuated by a single hydraulic system, yellow, green, or blue. Normally, the servos work simultaneously as a function of the commands coming from the all-speed ailerons or the ground spoiler control. The roll spoilers are actuated as soon as the all-speed aileron deflection angle exceeds 5 degrees. There are no jam detectors associated with the roll spoilers. Therefore, no jam warning lights illuminate with this malfunction. The roll spoiler's position is shown on the surface position scales of the flight control position indicator. The reading corresponds only to the outer and middle spoilers. The all-speed aileron position is directly read. The low-speed aileron position may be read on the same scale by depressing the low-speed aileron push button. A blue low-speed light comes on, indicating that the scale is showing low-speed ailerons. We'll now discuss the roll jam. First, if an individual servo package jams, say on the all-speed aileron, the other two units will cause the ailerons to move. The movement causes a microswitch to complete the circuit in a malfunctioning unit and illuminates a jam light in the cockpit, along with a single-stroke chime, and a servo's light on the master warning panel illuminates. If a jam occurs in the first officer's cable path, his yoke and cables will not move. Therefore, only the control surfaces on the left wing will move. The captain will need to apply a 34 to 90-pound force to override this jam. It's reasonable to assume there will be a reduction in response to the aircraft's roll rate. If the autopilot were connected, this jam would cause an autopilot disconnect. On the other hand, if the jam were located in the captain's controlled path, the first officer will have to exert enough force, 34 to 90-pound force, to override the jam. Again, the roll response would be reduced because the right wing's control surfaces are the only ones moving. The autopilot would disconnect with this jam. The autopilot is located attached to the left aileron differential unit. The autopilot, when connected, flies the controls on the left wing through the differential unit. The right wing control surfaces move through the spring strut located between the yokes. As both yokes move, all appropriate controls move on both wings. When the autopilot is engaged, two control wheel steering sensors allow changes of roll attitude by action on a control wheel known as control wheel steering function. The discussion continues with pitch control. Pitch control consists of two control channels running along each side of the fuselage. They are connected to the control columns by a forward override mechanism. They are also connected to the elevator system by an aft override mechanism and a solenoid locking device. When the yoke is moved back and forth, the inputs from the rods and cables to the cable quadrant and linkages to the individual actuators position valves to port hydraulic fluid from the hydraulic systems under pressure to move the elevator. Under normal operating condition, the coupling solenoid is uncoupled below 195 knots. The elevators, of course, move together because both cable quadrants are moving. At 195 knots or more, the solenoid locking device is engaged, and when one elevator moves, the other one moves also. This occurs because of the linkage between them. Now, if a cable path jam occurs between the yoke and the cable quadrant, the particular path will not move. However, the free yoke will move and position the cable quadrant to move the elevator. This requires a 112-pound force to override the jam system. With a single-channel operation, it is not possible to get full elevator travel. However, surface movement is more than adequate for pitch control. The autopilot will disconnect with either a captain's or a first officer's control path jam. Now, let's talk about an individual elevator jam. If the right elevator were jammed below 195 knots, the solenoid locking device is uncoupled, permitting the unjammed side to control pitch with either one or both columns. A force of 112 pounds force is required to override this aft jam. The autopilot will disconnect with this jam. Above 195 knots, the solenoid locking device is engaged and the good elevator is coupled to the jammed one. In this case, the columns will move against spring struts, but the elevator will not move. Pitch control is only accomplished with the stabilizer trim. The autopilot will disengage with this jam. Each elevator surface is actuated by 3 servo controls from 3 hydraulic systems, yellow, green, and blue. The servo controls are fitted with jam detectors, similar to the ailerons, which will illuminate the jam light on the servo control panel, accompanied by a single-stroke chime. The elevator surface position is shown on the L scale of the flight control position indicator. This position information is only picked off from the right elevator surface. Artificial feel units, known as pitch feel 1 and pitch feel 2, work in parallel to adjust the elevator forces according to speed and stabilizer position. The pitch feel 1 system receives speed information from ADC 1, and its feel actuator is supplied by the green hydraulic system. The pitch feel 2 system receives speed information from ADC 2, and its feel actuator is supplied by the yellow hydraulic system. Below 195 knots, the actuators are retracted and the artificial feel is only achieved by spring tension. Above 195 knots, the feel is provided by the actuator according to speed and stabilizer position. Pitch feel systems 1 and 2 work simultaneously or independently if one system becomes inoperative. In the case of loss of both systems, both actuators are brought back to the low-speed configuration corresponding to below 195 knots. Artificial feel controls and indicators are located on the pitch feel section of the overhead panel. Selection of each system is by a 2-position switch. With a selector position to on, the system is engaged. In off reset, system is disengaged. A pitch feel amber warning light illuminates if there is a system 1 or 2 failure. This is accompanied by a pitch feel light on the master warning panel and a single-stroke chime. An autopilot servo motor located in the stabilizer's right-hand side actuates the elevator control system. This servo motor has 2 actuators, one supplied by the green system and one by the yellow. When the autopilot is engaged, 2 control wheel steering sensors allow the pilot to change the pitch attitude by moving the control column. This is called control wheel steering or autopilot override. A detent unit allows the pilot to override the autopilot and limit the autopilot's authority in case of a runaway. Now we'll discuss the stabilizer control. Trimming in the pitch axis is achieved by displacement of the trimmable horizontal stabilizer to bring it permanently in line with the elevator. The stabilizer is actuated by 3 hydraulic motors. These motors operate a single jack screw linked to the stabilizer. The hydraulic motors may be controlled either mechanically or electrically. The mechanical control is achieved by the trim wheels via cable linkages which move the 3 hydraulic motors' pilot valves. The electrical control is achieved by 2 identical systems, pitch trim 1 and pitch trim 2. A trim computer for each system sends the signals to an electrical motor. The electrical motor actuates the hydraulic motor's pilot valve's control through a torque limiter. Engagement of each pitch trim system is achieved by means of the corresponding lever on the pitch trim panel. The lever is magnetically held in the 1 or 2 position. The corresponding system is engaged if the corresponding AC bus and the DC essential bus for pitch trim 1 or the DC normal bus for pitch trim 2 are supplied. It is also necessary that the corresponding ADC is available and the monitoring system of the corresponding computer is operative. The pitch trim computers receive flap position information. This information is used to vary the rate of trim speed. When both pitch trim systems are engaged, pitch trim 1 has priority and pitch trim 2 is in a standby and synchronized condition. There are two trimming modes, the electric trim and the auto trim. The electrical trim is used when the autopilot is not engaged. This moves the horizontal stabilizer setting by the action of the trim rocking levers located on the control wheels. The auto trim mode is achieved when the autopilot is engaged. The control wheel rocking levers are then inhibited for trim. The trim computers receive electrical signals from the autopilot. They control the horizontal stabilizer displacement until it is in line with the elevator. Thus, there is no jerk when the autopilot is disengaged. As soon as a pitch trim is engaged, and depending on the mode used, that is electric trim or auto trim, the trim system also provides Mach trim and alpha trim functions. Mach trim system is provided to vary the stabilizer setting to maintain aircraft stability. As the center of lift moves aft on the wing, tuck under starts to occur. The Mach trim computer compensates for this by trimming the stabilizer to as much as 1 degree 26 seconds aircraft nose up. Alpha trim protects the aircraft against flight effects at high angles of attack, high Mach number, and high altitudes. If the aircraft is banked sharply at high altitudes and speeds, the aircraft will tend to pitch up. Trim computers will sense this from information processed by the air data computer, Mach number, and trim. Trim input can be to a maximum of 1 degree aircraft nose down as required. We have already seen that with both trim systems engaged, the pitch trim 1 has priority and ensures the horizontal stabilizer displacement. Any detection failure triggers pitch trim 1 disengagement and pitch trim 2 takes over. Any failure of one or both systems is indicated by illumination of the pitch trim light on the master warning panel, accompanied by a single stroke chime and normally by the corresponding pitch trim lever dropping to the off position. All electric trim modes may be overridden by action on the trim wheels. Above a certain threshold, torque limiters send a signal to the computers, lending to both systems disengagement. Both systems may also be disengaged by setting both pitch trim levers to off. The position of the stabilizer is shown on the flight control position indicator. On the ground, if the horizontal stabilizer is not in the takeoff configuration, the stabilizer trim warning light illuminates on the flight control position indicator. If takeoff N1 is simulated, that's by pushing the takeoff configuration button, or throttles are moved above 97% N1, the config warning light illuminates on the master warning panel and the intermittent horn sounds. In the event one hydraulic motor pilot valve jams, the corresponding magnetic annunciator turns white on the test and monitoring panel. At the same time, the pitch trim light illuminates on the master warning panel and a single stroke chime sounds. The stabilizer trim rate is reduced. The yaw axes will be discussed now. The two sets of rudder pedals in the cockpit are connected together. A single cable path runs along the fuselage to mechanically connect the pedals to the 3 servo controls through a mechanical bell crank and a variable lever arm unit. The rudder position is shown on the flight control position indicator. The variable lever arm unit is a hydromechanical assembly. Its purpose is to progressively reduce the rudder travel according to the speed. For a given rudder pedal's displacement, the maximum rudder travel, which is 30 degrees up to 165 knots, is progressively reduced to a maximum of 5 degrees at 405 knots. The variable lever arm positions 3 servo actuators to cause hydraulic fluid under pressure to move the rudder. These servos are fitted with jam detectors similar to the ailerons and elevators. In this event, a jam light illuminates on the servo's control panel located on the overhead, and a single-stroke chime sounds. The servo's light on the master warning panel also illuminates. The rudder travel system includes two identical and independent systems operating in parallel, rudder travel 1 and rudder travel 2. Each system includes a hydraulic actuator which modifies the variable lever arm movement. Each actuator is slaved in position by one computer which receives speed information from the corresponding ADC. The rudder travel 1 actuator is supplied by the blue system. It is slaved in position according to speed information from ADC 1. The rudder travel 2 actuator is supplied by the yellow system. It is slaved in position according to speed information from ADC 2. These actuators are supplied through electro valves which are controlled by the selectors on the servo controls panel. At speeds below 165 knots, the actuators are shortened. The variable lever arm movement is not modified, so the rudder travel is not reduced. At speeds above 165 knots, the actuator lengthening is modulated according to the speed. The variable lever arm movement is modified by displacing the hinge point. So for a given rudder pedal's displacement, the rudder travel is reduced. When the rudder travel systems 1 and 2 are engaged, neither system has priority. Both actuators work simultaneously, but only the system which has the greater length assumes the function. The other actuator is synchronized. In the event of failure of one or both systems, the corresponding actuator is brought back to low-speed configuration by a spring strut. Each system engagement is achieved by a two-position switch on the rudder travel panel. With the switch positioned to on, the system is engaged. At off reset, it is disengaged. An amber rudder travel warning light illuminates for all detected failures within the corresponding system. It is accompanied by the illumination of a rudder travel light on the master warning panel and by a single-stroke chime. The rudder travel warning light can also be used to test the corresponding system. Trim control is mechanically achieved by direct action on the artificial feel, which consists of a spring strut. Thus, artificial feel is independent of the speed. The autopilot servo motor fitted downstream of the artificial feel is linked to the mechanical bell crank via a clutch system, allowing manual override. The servo motor includes two hydraulic actuators, one for each autopilot. One of the actuators is supplied by the green system and the other by the yellow system through electro valves controlled by the selectors on the servo control panel. A yaw damper servo motor is also linked to the mechanical bell crank. The yaw damper system provides lateral oscillations dampening and turn coordination in manual flight with the flaps extended, and a beginning of automatic rudder kick in case of an engine failure in automatic flight with the flaps extended. This is covered in the AFCS section. The servo motor includes two hydraulic actuators, each one operated by a different system. The yaw damper 1 actuator is supplied by the blue system and yaw damper 2 by the yellow system. The actuators are also supplied through the electro valves controlled by the selectors on the servo control panel. The engagement of each system is achieved by means of the corresponding lever on the yaw damper panel. The lever is mechanically held in the 1 or 2 position, and the corresponding system engagement is possible if the AC bus 1 and DC essential buses are supplied for yaw damper 1, and AC bus 2 and DC normal buses are supplied for yaw damper 2. The corresponding computer must be serviceable. The hydraulic supply is available, and one rudder travel system is operating. When both yaw damper systems are engaged, yaw damper 1 has priority and yaw damper 2 is synchronized. Failure of one or both systems is signaled by corresponding lever dropping to off and the illumination of a yaw damper light on a master warning panel, accompanied by a single-stroke chime. 3 additional notes that should be brought to your attention is rudder trim and autopilot inputs will move the rudder pedals. 2, yaw damper does not move the pedals. And the third one, when stall warnings are energized, the yaw damper inputs to the rudder for turn coordination is inhibited. This completes the primary controls. The secondary controls consist of high lift devices and lift dumping devices or spoilers. When the slat flap handle is moved in the cockpit, through rods and cables, inputs are made to 4 hydraulic motors, 2 for the flaps and 2 for the slat extension and retraction. These hydraulic motors move the trailing edge or leading edge devices by the use of 2 jack screws in each wing. The trailing edge flaps consist of 3 sections per wing. They are the double slotted type and move rearwards. Each flap section is driven by 2 jack screws and moves along 2 tracks. An actuating unit consisting of 2 hydraulic motors interconnected by a differential gear operates the flaps through a torque shaft assembly and jack screws. Each torque shaft assembly also drives an aileron droop signal unit. This unit allows the all-speed ailerons to deflect 10 degrees down when the flaps are extended. The leading edge slats, 3 sections per wing, move forward to reach their extended position. Like the flaps, for each wing, the 2 hydraulic motors interconnected by differential gear drive the slats through a torque shaft assembly and a jack screw. A Kruger flap and a notch flap are provided on each wing to improve the efficiency of the slats. They can be in 2 positions only, retracted or extended. Each of the Kruger and notch flaps is moved by a hydraulic actuator. These actuators are supplied through the green hydraulic system, through the same hydromechanical selector controlled by the input mechanism of the slat motors. A single 5-position control lever located on the center pedestal is used to operate the Kruger and notch flaps and to select the various deflection angles of the flaps and slats. The 5 positions are shown on this chart. You notice that the Kruger and notch flaps extend when the handle is moved from the first to the second position. The flaps start to extend at the 3rd position only. The control system consists of a duplicated cable linkage which gives commands to the pilot valves of each motor and to the Kruger and notch flap control selector through a clutch. This selector is controlled upstream of the slat motor unit. For each actuating unit and the selector, a cam box is provided to comply with the requirements for the extension of the corresponding control surfaces. Should a mechanical jamming occur between either the actuating unit and its clutch, the clutch disconnects and enables the opposite control surfaces to be used. Similarly, in the event of a jamming between the selector and its clutch, the slats and flaps will continue to operate. If the angle of attack exceeds 8.6 degrees, a solenoid will prevent the retraction of the slat handle beyond the 16-degree position until the angle of attack is reduced. As already mentioned, the flaps and slats are driven by 2 hydraulic motors. The flap motors are supplied respectively by the green and yellow hydraulic systems, and the slat motors by the green and blue hydraulic systems. The 2 hydraulic motors are independent, but they drive a single output shaft through a differential gear. Each motor is fitted with a hydromechanical brake which operates in low pressure condition. In normal operation, it is kept released by a hydraulic power passing through 2 series-connected electro valves. The flap motors are supplied directly from the high-pressure manifold through priority valves. The supply to the low-pressure brake is upstream of these valves. Similarly, the slat motors are supplied directly from the high-pressure manifolds through the priority valves. The supply to the low-pressure brake is upstream of these valves. Notice that the hydraulic supply to the slat and flap motors and the low-pressure brakes is not through the electro valves controlled by the selectors on the servo control panel. The Kruger and notch flap actuators, which use the green hydraulic system only, are also supplied directly from the high-pressure manifold through a priority valve. A jammed condition of a pilot valve in any slat or flap motor is indicated in the cockpit by a magnetic annunciator which turns white on the second officer's panel. At the same time, an electrical signal causes the closure of both electro valves of the brake of the corresponding motor. Cutting off the hydraulic supply puts the brakes on and locks the motor output. The movement is then provided by the other motor, but at a reduced rate. The position of the slats and flaps and the Kruger and notch flap configuration are displayed on the slats and flaps position indicator. The orange index on the flap scale displays the actual position of the control lever. It also indicates the limit speeds. The positions of the control surfaces are shown by the white stripes which move on the flaps and slats scales. A configuration light on the flight control position indicator illuminates on the ground only if the slats and flaps are not in a takeoff configuration. If takeoff thrust is used or simulated, for example, N1 greater than or equal to 97%, the configuration light illuminates on the master warning panel and an intermittent horn sounds. A Kruger light on the flight control position indicator gives the configuration of the Kruger and notch flaps. It is extinguished when the four control surfaces are retracted. The blue light flashes while in transit for any or all four control surfaces. The blue light is on steady when four control surfaces have reached their fully extended position. If 10 seconds after the movement signal, one or two Kruger and notch flaps are not in agreement with the position of the slat flap control lever, the Kruger light flashes continuously. The configuration light illuminates on the master warning panel, accompanied by a continuous horn. Note that in the event of a loss of the green system, these warnings will be activated at the slat extension. Two independent asymmetry computers receive slats or flaps position information from the detectors installed at the end of each torque shaft assembly. These computers compare the position of each shaft end and then allows the detection of any asymmetrical movement of the left and right wing control surfaces. This occurs when a 1-degree difference is detected between the left and the right wing. The computers cause the closure of both low-pressure brake electrovalves in each of the motors. The brakes lock the motor's output, which stops the control surfaces immediately. Only one monitoring channel is sufficient to provide this function. When an asymmetry has been detected by at least one of the computers, and if both brakes have operated, the asymmetry light illuminates on the surface position indicator together with a configuration light on the master warning panel. A continuous horn sounds. The position of the involved control surface is indicated on the flight control position indicator. Also, in the event of a complete hydraulic failure to the slats or flaps, for example, open lines, the flaps or slats will stop where the failure occurred. Either one stops because they extend and retract by a jack screw arrangement, and aerodynamic forces would not be able to override this jack screw. Let's study the speed brakes and the ground spoilers now. Speed brakes are provided for in-flight, and ground spoilers are used on the ground. In each wing, the speed brake function is provided by two inner speed brakes and 2 outer speed brakes. The ground spoiler function is provided by 4 speed brakes plus 3 roll spoilers on each wing. The speed brake handle, which is located on the center pedestal, is moved between the retract and full position to operate the speed brakes. A linkage transmits the movement of the handle to the pilot valves of the speed brake servo controls. Each speed brake is actuated by a single servo control as opposed to all the other control surfaces. The 2 servos for the 4 speed brake panels on each wing are supplied by the blue and the yellow hydraulic systems. The speed brake servo controls are supplied through electrovalves controlled by selectors on the servo control panel. Just a reminder that the speed brakes are not fitted with jam detectors. A speed brake light located on the flight control position indicator gives the speed brake configuration. It is off if the speed brakes are retracted. It illuminates amber as soon as the speed brakes are extended. On the ground, if the speed brakes are extended and the takeoff thrust is applied or simulated, for example, N1 greater than or equal to 97%, the config light illuminates on the master warning panel accompanied by the intermittent horn. The maximum speed brakes deflection angle in flight are 35 degrees for the outer speed brakes and 25 degrees for the inner speed brakes. The ground spoiler function is next. The inner speed brakes extend to 50 degrees and the outer speed brakes extend to 35 degrees. The roll spoilers extend to 50 degrees. This occurs either at landing or in the event of an aborted takeoff. Ground spoilers will extend automatically if the following conditions are satisfied. The function has been armed, both throttles are at idle, and the aircraft is in the ground configuration. Ground spoilers are normally armed by pulling the speed brake control lever upwards when at the retracted position. Arming is also accomplished when either reverse lever is unlocked. The ground condition is achieved using the speed information coming from the tach generators on the rear, right, and left wheels of each main landing gear. The logic is such that the ground condition is achieved when landing if the speed of at least one wheel of either main landing gear is greater than 50 knots. If a takeoff is aborted beyond 50 knots and weight is still on the main gear, the spoilers will extend as reverse is applied. The electronic logic supplied an unlocking solenoid and an electric actuator. The solenoid releases the control handle, and the handle is driven by the electric actuator to the extend position. The movement of the handle is transmitted to the mechanical linkage, causing the ground spoilers to extend. Extension of the ground spoilers is carried out in 2 phases. When the handle moves from retract to full, the normal extension of the speed brakes is controlled by the electric actuators. From full to ground spoiler, the complete travel of the linkage causes the opening of a hydromechanical selector. This hydromechanical selector is supplied by the yellow hydraulic system and allows 2 actuators per wing, one for the speed brakes and one for the roll spoilers, to extend on the ground for full deployment of all 7 spoiler panels on each wing. These actuators cause the extension of the inner speed brakes from 25 to 50 degrees and the roll spoilers directly from 0 to 50 degrees. Ground spoiler extension is indicated on a slat flap position indicator by the illumination of the speed brake light, and on the flight control position indicator by the indices on the spoiler scales. Please look at the diagram and note that the spoiler indication does not take into consideration the position of the inner roll spoiler, which uses the yellow hydraulic system. This completes the flight control presentation.
This program is intended to review procedures relating to Omega system operations. Procedures such as initialization and waypoint entry will not be discussed since they are now routine. During system operation, certain malfunctions and/or failures may occur. The LTN-211's built-in test system monitors and tests approximately 10 functions. The probability of detecting a failure within the system is greater than 99%. Whenever the display selector switch is set to DTK STS, the right numerical display indicates action malfunction codes and the status of the system. The status indication consists of a 2-digit coded number in the least significant digits. The red warn enunciator illuminates when an Omega navigation system failure has been detected by the integrity monitoring function. A steady warn enunciator indicates a hard ONS failure. When this condition occurs, attempt system reinitialization. If it fails again, report malfunction to maintenance. The logbook write-up should include the following: the Z time at which the malfunction occurred. The stations being used is indicated when the CDU display selector is set to STA. The wind and true airspeed readouts from the CDU. The malfunction code, as discussed later in this program, and finally, a brief description of the problem. A flashing warn indicates that operator action is required and will indicate failure of a subassembly, loss of aircraft inputs, magnetic heading, and/or true airspeed, or insufficient input data by the operator. Should a flashing warn appear, set the display switch to DTK STS and note the action code, A2 in this example, in the left half of the right display. The flashing warn may be extinguished, if desired, as indicated in the following discussion on malfunction codes. Pressing the hold push button will result in a malfunction code replacing the action code in the right display, should there be more than one malfunction present. Repeated pressing of the hold push button will display these additional codes. After all malfunctions have been displayed as indicated by a 00 appearing in the right numerical display, subsequent pressing of the hold push button will again result in display of the action code. A copy of this action and malfunction code table is printed in your flight manual. If the malfunction code indicates a problem associated with the air data computer system, switching to the opposite ADC may resolve the problem. On Eastern Airlines L1011, switching may be accomplished by using the Omega switching unit mounted just below the CDU. Be warned that when ADC input is switched, the wind goes to 0 and then builds to the actual wind based on the new air data computer true airspeed. This causes the wind readout to be invalid for 15 minutes. Do not use winds derived by the Omega system for 15 minutes after switching ADC inputs. If changing the ADC input does not solve the problem, manual entry of true airspeed may be accomplished. The man, meaning manual, enunciator will be illuminated to show that the operator has manually entered one or all of several parameters required to maintain Omega navigation. Values that can be entered manually are true airspeed, magnetic heading, and cross-track offset. The manual enunciator may also be illuminated at the same time as a flashing warn enunciator whenever valid true airspeed and/or magnetic heading are not available. Manual entry of true airspeed and/or magnetic heading will cause the warn enunciator to extinguish. The manual annunciator will remain on until the manual entries have been set to 0 by the operator. The LTN 211 requires both true airspeed and heading as inputs from the aircraft. In the event that one of these inputs is lost during flight, these values may be manually entered and updated as a backup mode of operation. For manual entry, set the display selector switch to mag heading, true airspeed. Press L key for heading or R for true airspeed. Key in desired data, heading in left display, true airspeed in right display. Press ENT for enter. Flashing warn will go out and manual annunciator will illuminate. Update the inserted values as necessary until valid sensor inputs are restored. Note, the loss of heading or true airspeed inputs will be enunciated by the flashing warn and verified by an action code. The manual annunciator will remain illuminated until valid aircraft signals are available and manual entries have been set to 0 by the operator. When in the DR mode, an extended period of time, it may become necessary to manually update wind direction and/or velocity. The winds shown on the computerized flight plan may be used if, to this point, they were accurate. For a manual wind direction entry, set the display selector switch to wind, then press L. Then starting with the most significant digit, key in the direction and press ENT. For a manual velocity entry, press R. Then starting with the most significant digit, key in velocity and press ENT. Note, wind entry requires the entry of both wind direction and wind speed. A manual entry of wind is only possible in the DR mode, and the system will automatically use the calculated value for wind when Omega navigation is resumed. This aux function is used only in the DR mode to manually enter drift angle and ground speed. In flight, these parameters must be periodically updated to maintain accurate DR navigation. Here again, your computerized flight plan may be used as a data source. When Omega navigation is resumed, these values will be automatically updated based on received Omega data. Manual entry of drift angle and ground speed may be accomplished as follows. Verify that the system is in the DR mode, status 03. Set the display selector to aux and the WPT switch to 1. Press the L push button. Left display blanks and ENT comes on. Press the R or L push button to indicate drift angle either right or left of track. Enter drift angle to nearest tenth of a degree and press the ENT push button. Note, drift angle must be less than 39.9 degrees. Press R push button. Right display blanks and ENT comes on. Enter ground speed to the nearest knot and press ENT. Verify that entered data is correct and that value of calculated wind is reasonable. A steady DR annunciator indicates that the ONS is in a dead reckoning mode. The ONS would normally be in Omega navigation mode rather than DR. When this condition occurs, set the display switch to the desired track status and check for an action malfunction code in the right display. If a code exists, take the corrective action specified. If there is no code displayed, set display selector to the station and check station signal quality. The ambiguity annunciator will be illuminated during navigate mode to indicate that the ONS has detected an ambiguity between calculated present position and displayed present position. The AMB annunciator will go out when the condition disappears. The operator should perform a precision position update. Consult your flight manual for precision update procedures when it is necessary to update the system. Take time now to review pertinent sections of Volume 1 with your instructor, and finally, review the abnormal procedures in your flight manual. This ends the Omega Recurrent Audio-Visual program.
The Auto Flight Control System, or AFCS as we shall refer to it, will be presented in 3 sections. Part 1 will include general information and system description. Part 2, a discussion of controls and indicators, and Part 3, an operational sample. General information and system description. The AFCS provides manual or automatic modes of aircraft control throughout the envelope and is comprised of the following: 2 yaw dampers, 2 pitch trim systems, 1 auto throttle system, 2 integrated autopilot and flight director systems with altitude alert, and 1 speed reference system. The systems are self-monitored to provide fail-passive capability. This is the ability to detect a fault, provide a warning, and automatically disengage the autopilot before it affects the aircraft landing or flight path. The fail operational assembly consists of 2 fail-passive systems. In this case, an automatic changeover device selects the signal of the valid system. One system has command, and there is an automatic changeover to the other when one system fails, and the approach may be continued. The A300 has the fail operational system, which is required for Category 3A. The yaw damper uses 3 different input signals: the yaw gyro signal, the roll attitude signal, and the lateral accelerometers. The yaw rate signal controls the Dutch roll damping and damping of effects of turbulence mode. The roll attitude input controls the turn coordination mode. With the autopilot engaged, the accelerometers counter the immediate effects of an engine failure. As a result, the lateral movement caused is detected and a continuous rudder correction is applied. In summary, the yaw damper operates in much the same manner on the A300 as on other aircraft Eastern operates. The yaw damper rudder deflection is limited to 10 degrees or less depending on aircraft speed. Now, with the autopilot engaged and the flaps at 8 degrees or more, the accelerometers will provide short-term rudder deflection, while the long-term deflection for engine failure compensation is provided by the autopilot yaw channel and is limited only by the rudder travel system. The yaw damper engage switches are located on the overhead panel. There are 2 identical subsystems for redundancy in the event of one failing. The pitch trim subsystem actuates the trimmable horizontal stabilizer. When the pilot activates the control wheel trim switches or rocker switches, he causes the electrical trim function to operate the horizontal stabilizer. With the autopilot engaged, the electrical trim function will automatically trim the horizontal stabilizer. This is a dual subsystem for redundancy. The auto throttle subsystem moves the throttles in order to maintain the airspeed selected on the counter. The indices or bug in both airspeed indicators will also point to the same speed. The auto throttle system moves the throttle levers to acquire the selected speed. Its second purpose is the holding of selected N1 displayed on the N1 computer. The autopilot flight director subsystems use a common computer and employs the same electronic computation. The autopilot flight director is controlled from a common panel, and most of the time they operate in the same modes. We will therefore assume that the autopilot simply obeys the flight director commands as a human pilot responds to flight director command indications. The Failure Performance Indicator, or FPI, indicates the mode and function engagement configuration. From left to right, the indications concerning the auto throttle, then lateral autopilot flight director modes. The lower part displays the approach and automatic landing annunciators. The altitude alert system provides audio and visual warnings on approaching or leaving a pre-selected altitude. It operates independently of autopilot or flight director engagement modes. The system is operative when the landing gear is retracted or when the aircraft is on the ground. The Speed Reference System, or SRS, provides two functions: the speed acquisition and maintaining function, and the alpha floor function, which protects the aircraft at high angles of attack. The SRS, speed acquisition and holding function, is used for takeoff and for manual overshoot. It is engaged by pulling up on one or both go levers under the throttle levers. The SRS light on the upper part of the failure performance indicator illuminates green and will remain on until the autopilot or flight director upper mode is engaged. The term upper mode refers to any input to the flight director or autopilot by the pilot using the push buttons on the AFCS control panel. Speed acquisition and maintaining function is used to maintain the speed set on the speed counter on the autothrottle panel. The commands are displayed on the attitude director indicator pitch bars. These commands enable the pilot to acquire and hold the selected speed. An important point to remember is it is available when the autopilot and flight directors are not or are engaged and no upper mode is selected. The alpha floor function is automatically activated when the aircraft incurs a high angle of attack. The autothrottles will then move to the setting on the N1 computer. The operation of all the above subsystems requires AC and DC power supplies, the blue, green, and yellow hydraulic systems pressures, and the operating condition of the computers and associated systems. The AFCS control panel is located on the glare shield above the pilot's forward and center instrument panels. Associated with the AFCS are two failure performance indicators, or FPIs. They display the various operative modes and conditions. We will now study the action of the different controls and indicators, starting with the flight director. Flight director operation is controlled by depressing FD1 or FD2 push buttons. The selected flight director push button will illuminate. Only one flight director can be engaged at a time, except in an approach or land modes. When flight director 1 push button is pressed, the captain's flight director system is activated, and FD1 appears in his ADI. 1 also appears in the HSI. This means that NAV1 is supplied to the captain's complete flight director system. The figure 1 also appears in the first officer's ADI with the same selection. However, 2 appears in his HSI. Remember that only one flight director is activated at a time, and NAV2 is supplying the first officer's HSI. The only time 2 flight directors can be engaged at the same time is when approach or land modes have been selected. When number 2 flight director is engaged, 2 appears in both the first officer's instruments. The reverse is true, then, on the captain's side. Number 2 appears in his ADI, while number 1 appears in his HSI. In summary, the flight director that is pressed supplies both ADIs. The HSI is supplied by the respective nav receiver. If the captain's nav receiver has failed and the navs have been switched, number 2 will appear in both HSIs. The only time you can have the same figure, whether it's 1 or 2, appearing in both HSIs is by switching the nav receivers. The FD bars switch is located on the glare shield in front of each pilot. When the switch is positioned off, the pitch and roll bars are biased from view. For example, if the captain is flying, the first officer could position his FD bar switch off, and the bars will disappear from his ADI. Our discussion of the controls and indicators on the AFCS will be with reference to the flight director only. Later, we'll add the autopilot. This means that in all cases, the pilot must fly the aircraft to satisfy the commands as displayed on the pitch and roll bars to achieve that which was selected. The heading select mode is established by pressing the heading select push button. A flight director push button light and green triangle in the heading button will be illuminated. Also, green heading select light is illuminated in the failure performance indicator. The flight director roll bar will display commands to turn to the bug setting in the HSIs, which correspond to the settings on the counter. The bugs in both HSIs are set by this single counter located on the glare shield. The pilot flies the aircraft to satisfy the commands. The roll bar will be centered when the required bank angle is achieved and will provide commands to roll out on the selected heading. The heading mode is similar to the heading mode in our other aircraft and is compatible with the pre-capture phases of the VOR, localizer, approach, and land modes. With a VOR or localizer frequency selected on the associated nav receiver and a course selected in the course window, pressing the VL button will engage the VOR-LOC mode. When the course knob is moved, the split course arrow or course pointer in the respective HSI will move to the same figure that appears in the course window. VL amber will appear in both failure performance indicators. The roll command bar in each ADI will provide visual cues to capture and maintain the desired course. At VOR radio or localizer capture, VL amber changes to VL green and the heading select legend will disappear. The pilot follows the commands on the roll bar to capture the desired course once the appropriate angle of intercept has been established. When used as an ILS, set the course arrow for the inbound front course heading, whether it is a front or back course approach that is to be flown. In this mode, an ILS approach to a runway that has no glide slope can be made without a glide slope flag in view. A reminder with respect to the course bar. It is directional. However, the roll bar in the ADI will display commands to turn to the course arrow head. Therefore, for a back course, the flight director switch should be turned off. The glide slope arrow is located on the right-hand side of both the ADI and HSI. The runway in the ADI is an expanded version of the course deviation bar in the HSI. The vertical speed mode is used to provide a reference rate of climb. It's displayed on both ADIs by a pitch bar. The pilot can adjust the pitch bar to change the pitch reference and thus the rate with the vertical speed thumb wheel located on the AFCS panel. The failure performance indicator will show a green vert speed legend when the vertical speed push button is pressed. The indicated airspeed mode is a pitch mode. That is to say that the aircraft pitch angle is increased or decreased to maintain the indicated airspeed at the time of engagement. The mode is established by pressing the IAS push button. Indicated airspeed mode is a climb and descent mode. The failure performance indicator will have an IAS green legend light illuminated. Remember, this is a pitch mode and is not compatible with any other pitch mode. The pilot flies the aircraft to the pitch bar to hold the desired airspeed. The approach mode on the A300 operates the same as it does on other aircraft that EAL operates. It allows capture and tracking of the localizer and glide slope. There is an arming phase and capture phase indicated by amber and green lights respectively. These legends appear on the failure performance indicator. The bearing inbound or inbound localizer course is selected on the course module. When the approach mode is selected, two flight directors can be engaged. The capabilities are: one flight director engage, approach 1 appears in the FPI. Two flight directors engage, approach 2 appears in the legend. Two flight directors and one autopilot engaged, approach 1 appears in the FPI. Do not confuse approach 1 or 2 appearing in the FPI with category 1 or 2 approaches. They are not synonymous. At this point, the subjects of supervisory override and autopilot override will be addressed. Supervisory override allows the control wheel inputs to be applied to the autopilot flight director computers. The computers then feed the servos and the autopilot flies the airplane. This applies only in certain modes: altitude acquire green, VL green, approach mode or vertical speed, and land mode when the aircraft is above 700 feet radial altitude. Autopilot override is a situation in which control wheel input bypasses the autopilot flight director computers and is applied directly to the servos. This occurs in all other autopilot modes. The pilot can feel this through the amount of force which is required in both the roll and pitch axes to override the autopilot inputs. The autopilot will not disengage, nor will any selected mode drop out as a result of either supervisory or autopilot override. The items discussed thus far, that is heading select, VOR loc, vertical speed, IAS, and approach modes, have been in relation to the flight director. The aircraft must be flown manually to satisfy the commands on the pitch and roll bars in order to achieve that which was selected. With the autopilot engaged in command, upper mode signals are now sent to the servos, and the autopilot flies these same selected commands. The pilot monitors the operation on the flight director and FPI. The land mode is common to both pitch and roll axes. It is an autopilot command mode only and is used for auto landings. It is the only mode that allows engagement of both autopilots. The FPI will display Land 2 or Land 3 depending on whether one or two autopilots are engaged. This operation is described in the Category 3A slide tape program. The altitude module provides control in two modes: the altitude hold mode and altitude acquire. When the altitude hold mode is engaged, the pitch bar provides commands to hold the barometric altitude at the time of engagement. In the flight director mode, the pilot must fly the aircraft to the pitch bar. The autopilot will hold the altitude when it is engaged. No counter setting is required for this mode. The altitude acquire mode is used when a climb or descent to a pre-selected altitude is to be made. The altitude hold mode engages automatically when the pre-selected altitude is captured. Again, in flight director mode, the pilot must manually fly the aircraft to the pitch bar. With the autopilot engaged, the airplane will level off at the selected altitude. Caution. If with the altitude hold mode engaged, altitude acquire push button is pressed, the altitude acquire light illuminates green in the FPI. The aircraft will then fly to the selected altitude at a constant vertical speed of 1,000 feet per minute. This, in fact, is a vertical speed mode for automatic altitude transition. Upon reaching the selected altitude, the airplane will level off and the altitude hold mode is automatically engaged if the autopilot is engaged. Pitch bar displays commands to fly in the flight director mode. Two altimetric reference lights provide reference to which autopilot flight director computer is supplying the altitude logic. Captain's light illuminates when autopilot flight director 1 is engaged. First officer's light illuminates when autopilot flight director number 2 is engaged. The captain's number 2 altimeter always supplies the barometric correction. The autothrottle system permits the speed to be controlled by means of a speed select mode and the maximum N1 to be maintained by means of the N1 mode. In both modes, the RPM is limited to protect the engines. At any time, the crew can override the system by manually moving the throttle levers without disengaging the autothrottles. When the autothrottle lever is moved to the magnetically held up position, the autothrottle computer is armed but is not supplying inputs. When the speed select, or N1, is illuminated, the autothrottles will set the thrust as necessary to acquire and hold either the selected speed or the N1 setting. When speed select mode is engaged, aircraft speed is changed by selecting the desired speed in the counter. This also moves the bugs in the airspeed indicator. In speed select mode, the autopilot land mode is engaged, and automatic throttle closure is initiated at 20 feet. The N1 is a full power mode used for takeoff, climb, manual overshoot, automatic go-around, and alpha floor functions. Alpha floor protection is provided when the SRS is operative, the autothrottle system is armed, and the radio altimeter is 100 feet or more, at a preset angle of attack, or when differential acceleration caused by wind shear is detected. SRS automatically switches the autothrottle to the N1 mode. The throttles adjust to acquire and maintain the N1 RPM for the mode selected on the N1 limit computer, and the N1 flashes in both FPIs. Additionally, the autothrottle system provides fast-slow indication in both ADIs, which is a deviation from the selected speed set on the counter. The autothrottles do not have to be armed for this function. On takeoff or go-around, SRS pitch bar and the fast-slow indication will provide reference for V2 plus 10 with both engines operating, or V2 with an engine out. Of course, V2 is V-select, which is manually set in the counter window by the pilot. In summary, with the autothrottle lever in the arm position and N1 selected, the autothrottle system will move the throttles to the settings selected on the N1 computer. For either maximum takeoff or flex takeoff, Once the power has been obtained with a wheel spin-up of more than 60 knots, the auto throttles declutch until a climb mode is pressed. When N1 or speed select is pressed, the FPI reflects the mode by displaying either the speed select or N1 legend. The auto throttles are disengaged by buttons on either outboard end of the throttle levers. The auto throttles are also disengaged when the interlocks are not satisfied. For example, rotating the AC Essential bus selector out of the normal position. When indicated airspeed hold is selected, the auto throttle speed select mode is disengaged because, you'll recall that, IAS is a pitch hold mode. In other words, the body angle changes in order to maintain the speed. However, in auto throttle mode, the throttle levers move to change speed. These two situations are conflicting and therefore not compatible. If a go-around is initiated with the autopilot off, the flight director will disengage and the ADI pitch bars will be supplied by SRS. SRS will be illuminated in the FPI. With the flaps extended more than 8 degrees and at least one autopilot in command, lifting either go lever engages the go-around mode. The go-around mode is an autopilot mode only. Go-around appears in both FPIs. If both autopilots are engaged in land mode and go-around is selected more than 700 feet radio altitude, the second autopilot will disengage. If less than 700 feet radio altitude, both remain engaged until go-around is disengaged by selecting an upper mode. Turbulence mode is selected with the autopilot engaged by pushing rocker switches on either pilot's control column. The autopilot returns to the pitch attitude hold mode, disengaging IAS, altitude or altitude acquire. The auto trim rate is reduced. The flight director pitch bars disappear and the upper modes are canceled. The word turb appears in the FPI. The turbulence mode is canceled by reselecting altitude hold, then followed by pushing altitude acquire so that the aircraft may return to the altitude prior to turbulence encounter. The autopilot has a control wheel steering function which allows pitch and/or roll attitude changes by using control column and yoke without disconnecting the autopilot. The autopilot can be overridden during a capture phase. When the pilot moves a control column, a threshold load detector senses the load. It then transmits a signal to the autopilot computer, which changes the longitudinal attitude when the load is released. The autopilot then takes into account the new attitude and holds it. The principle is the same for the lateral axis. With either the supervisory override function or control wheel steering, the load on the controls introduced by the pilot is detected by a load detector on each axis. These detectors transmit signals to the autopilot flight director computers, which then cause a change in lateral attitude. When the load is released, the autopilot stabilizes in the new flight path. The longitudinal attitude operates in the same manner. When a VOR or localizer capture is made late, the supervisory override function permits the pilot to modify the computed path in order to avoid an overshoot. The autopilot can be engaged in two different modes. In manual, the autopilot only operates in the basic modes. That is to say that it holds pitch and roll attitudes. Control wheel steering is available all the time, and the associated flight director can be engaged and upper modes selected. However, in this case, the ADI bars give commands according to the mode selected, independently of the autopilot. The pilot can then follow the commands computed by the flight director by using control wheel steering. In command, the autopilot flies the aircraft by acting on all three axes by means of information processed by the autopilot flight director computer, like a human pilot, according to the mode selected by this human pilot. When an autopilot is engaged in command, the corresponding flight director is automatically engaged. Both autopilots can only be engaged simultaneously when the land mode is selected and glide slope captured has occurred. In normal operation, the autopilot is used in command position only. Both flight directors can be engaged when either approach or land mode is selected. On autopilot engagement, either in manual or command, the system holds the pitch attitude of the aircraft. If the autopilot is engaged in command and the roll light illuminates green in the FPI, the pitch, hold, and roll mode will engage when the autopilot is engaged, or with no upper mode selected, or by moving one of the pitch trim rocking levers. Each autopilot may be disengaged by setting the associated lever off. Both autopilots may be disengaged with the disconnect button on the outboard horn of each pilot's control column. Also, either autopilot will disengage automatically when a failure is detected in the computers. To reduce the computer internal temperature when the aircraft is on the ground, the computer electrical power supply is removed 80 seconds after the last engine is shut down. The reference signal is from the oil pressure switch and time delay. As was previously explained, the FPI is used to monitor normal and abnormal indications. We will explain the legend starting with NAV. NAV is illuminated anytime the autopilot flight director computers are coupled to the Omega. This is regardless of the position of the captain's or first officer's ONS, VOR LOC switch. The Omega is explained in its presentation. The speed reference system, you'll recall, is a flight director takeoff or go-around mode only. It is activated by action on the go levers. The SRS illuminates in the FPI. Conversely, go-around is an autopilot mode. When go-around is selected above 700 feet, the land mode is pressed. One autopilot lever moves to off. Below 700 feet, both stay connected, making dual autopilot go-around until an upper mode is selected. For example, flight director or heading or altitude. Manual is illuminated when either autopilot is selected to manual. This is a control wheel steering or CWS mode. No upper mode can be selected for autopilot use. However, the upper modes can be used for flight director. In command position, the upper mode can be selected for autopilot use. If no upper mode is selected, the autopilot is in a CWS mode even though the lever is in the command position. When a flight director is engaged and an upper mode is selected, the pitch bar is in view in the ADI displaying the selected commands. When the heading select push button is pressed, the roll bar appears in the ADI, and if the roll commands are satisfied, the aircraft will turn to the selected heading. Pressing the IAS hold push button will engage indicated airspeed hold mode. The pilot flies the aircraft to satisfy the commands on the pitch bar, or if the autopilot is engaged, the airspeed that existed at the time of selection will be held. If altitude push button is pressed and altitude green light is illuminated, the IAS mode would disengage, and now the autopilot will fly the aircraft to hold the altitude. With the flight director only engaged, the pilot flies the aircraft to the pitch bar to accomplish the same thing. Altitude acquire amber light means the altitude acquire push button has been pressed to arm the system to capture a pre-selected altitude. In flight director mode, you fly the commands as displayed on the pitch bar. If the autopilot is engaged, it will capture the altitude automatically. Altitude acquire green is a capture phase after arming. The capture begins approximately 1/3 the rate of climb or descent before the desired altitude. At the altitude acquire green light goes out and altitude green is illuminated. The turbulence mode is peculiar to the autopilot only and concerns the pitch axis. As the name implies, it is used in moderate or severe turbulence. VL and GS amber lights indicate that approach or land has been selected and the aircraft has not captured the VOR radial only or the localizer and glide slope. This is an arming phase. When the radial or localizer and glide slope is captured, the legends turn green. The vertical speed push button is used to select the autopilot flight director vertical speed mode. The rate of climb or descent is controlled by the thumb wheel located adjacent to the push button. The rate setting is red on the indicator next to it. Roll is an autopilot mode only. No upper mode need be selected. The autopilot will hold the bank if more than 5 degrees and pitch at the time of engagement. Roll legend is illuminated in the FPI. The throttle off light illuminates when either N1 or speed select is tripped off. However, the auto throttle lever will remain in the arm position and the auto throttle computer is still powered. Speed select, when on, means the throttles and airspeed are controlled by selecting the speed on a counter. When N1 is illuminated, the throttle levers move to the selection on the N1 computer, for example, takeoff, climb, etc. When land arm amber legend is illuminated, it means that land mode has been selected and one autopilot is flying the aircraft. 2 autopilots can be engaged. When land arm amber turns green at 700 feet, both autopilots are flying the aircraft with full monitoring. At this time, VL and GS green lights extinguish in the FPI. The flare light illuminates at 50 feet, indicating that the autopilot flight director computers are in a flare and land mode. All circuits are functioning and the autopilot will flare and land the aircraft. Rollout will illuminate when the wheel's spin reaches 50 knots or more. At 30 feet, the yaw pointer appears in the ADI and is the primary instrument for keeping the airplane aligned on the center line of the runway. Approach 1 illuminates with approach selected. 1 flight director and 1 autopilot, or 2 flight directors and 1 autopilot. Approach 2 is illuminated with only 2 flight directors engaged. Land 2 illuminates with land mode selected and 2 flight directors and 1 autopilot engaged. After glide slope capture, the second autopilot is engaged and land 3 is illuminated. The align light indicates a failure detected in the alignment circuit, or with both autopilots engaged, a discrepancy between course settings. The lights on the glare shield can be dimmed by means of a selector to the left of the auto throttle panel. The inner knob controls glare shield integral lighting at varied settings. The outer knob controls mode selection push buttons. An operational sample. The following sample is a suggestion for the orderly use of the AFCS from takeoff to approach. The approach and landing part is discussed in Category 3 program. When the aircraft is ready to take the runway, the letters FHA should be the thought. F is a reminder that the appropriate flight director should be pushed on. H for the selecting the runway heading on the bug and pressing the heading switch light. The letter A for setting the first assigned altitude in the window, then depressing altitude acquire push light. If the departure heading is other than the runway heading, it may be preset in the window and the heading push button pressed after takeoff when the turn is to be made. The auto throttle system lever is positioned up and takeoff setting either flex or max is punched into the N1 computer. Also ensure V2 is selected in the speed window and bug set on the standby airspeed indicator. When the power is advanced for takeoff, as N1 indicates 60%, activate the go levers. The auto throttle systems will move the throttles to the selected takeoff setting. Once the takeoff power has been established, the auto throttles will declutch. The selection remains on the push buttons, and the FPI should have SRS and N1 green lights on. Rotate the aircraft at VR until the pitch bar is centered. This will maintain a speed of V-select plus 10 knots, which is V2 plus 10 knots. The pitch angle should be limited to 18 degrees. At 500 feet, the autopilot can be engaged. At 1,000 feet, select climb or cruise power on the N1 computer, and while following the SRS pitch commands, the rate of climb will be 1,000 feet per minute and the body angle will be approximately 10 degrees. As the flaps are retracted at V3, ask to be bugged to VFTO. With the aircraft cleaned up, ask to be bugged to 250. You're still flying the pitch bar and SRS. As the aircraft accelerates to 250 knots, press IAS hold push button. IAS illuminates in the FPI and SRS disengages, and these legends are illuminated. When you climb through 10,000 feet, press the vertical speed push button and roll the thumb wheel to flatten out the body angle. This causes the airspeed to increase. When the normal climb speed of 300 knots is obtained, press the IAS push button again. With N1 and IAS mode selected, the aircraft will climb at 300 knots. The autopilot flies the aircraft in pitch axis to maintain the selected speed while thrust is maintained at the required climb power. When altitude acquired turns green, indicating the capture phase, the speed select counter is moved to the appropriate speed and speed select push button is pressed. This is the only time that speed select is used in climb. Speed select can be made when altitude acquired green is illuminated. Also is used in cruise within the terminal area and landing. Use IAS in descent. The approach and landing phase is explained in the Category 3A program.
This presentation identifies the airport and ground facilities, airborne systems, training requirements, and operational requirements that must be satisfied to utilize Cat 3 minimums. This information has been extracted from the FAA Advisory Circular and the A300 Flight Manual. Let's begin with definitions. A Category 3 operation is an instrument approach with no decision height limitation and with a required RVR of not less than 600 feet. An alert height is a height above which a Category 3 approach will be discontinued and a missed approach executed if a failure occurs in one of the required redundant operational systems in the aircraft or in the ground equipment. An alert height of 100 feet has been established for the Eastern Airlines A300 aircraft. An automatic fail operational Category 3 system provides redundant operational capability using automatic systems. If one of the automatic systems fails below the alert height, the flare and touchdown may be accomplished using the remaining automatic system. The Category 3 operational concept provides that the total airborne system must be designed to provide sufficient information to the pilot so that the landing may be safely continued and completed, or a go-round safely executed from any altitude following any single failure or combination of failures not shown to be extremely improbable. The A300 meets this requirement in its design and certification. A300 Cat 3 operations will be auto-land with Land 3 capability. The pilots are required to monitor the computers once they have programmed the auto-land system. According to the advisory circular, users of U.S. airports may be authorized to use minima as low as 600 RVR at designated Cat 3 airports, which meet the following prescribed criteria. The ground-based system must have failure survival capabilities such that total loss of guidance will be extremely improbable. The ground ILS must meet Category 3 requirements. The approach light system requirements are the same as for Category 2 operations. Touchdown zone lights are required. Centerline lights are required with appropriate distance to go coding. Precision instrument runway markings are required. 3 RVR transmissometers are required, unless it can be shown that 2 transmissometers can meet the operational needs for a particular airport. An issuance of a Cat 3 approach plate indicates that the existing RVR system meets the criteria. Positive voice communication to the pilot is required to advise of sudden RVR changes. A system which provides positive control over aircraft and vehicles to ensure runway and critical ILS areas are kept sterile is required. The obstacle clearance requirements are the same as for Category 2 operations. Simply stated, a Category 3 approach plate indicates that the particular airport meets all the requirements for a Category 3 approach. The following airborne equipment is provided in the A300 aircraft to meet Category 3 requirements. All of the required equipment listed must be operating down to the alert height of 100 feet. The required equipment is listed in the N19 section of the A300 flight manual. The provisions are as follows. For Land 3 capability, 2 autopilots in command mode and a flight director with 2 displays. 2 autopilot off lights. Instrument failure warning system with flag warnings of instrument failure. Beam deviation warning lights and auto land lights. 2 ILS receivers. 2 radio altimeters. The A300 has a monitor system which indicates malfunctions or failures in the instruments, automatic flight controls, or other systems. Auto throttles must be engaged in the speed select mode. A missed approach attitude guidance system, which may consist of either an ADI pitch display, a flight director pitch command, or an automatic go-around system is required. The use of auto go-around is recommended. Rain removal capability. Redundant flight control systems are installed on the A300 along with 2 pitch trim systems and 2 yaw damper systems. The yaw damper will provide rollout guidance. Rollout operation is monitored by the yaw pointer at the top of the ADI. Illumination of a line on the FPIs will indicate alignment and rollout phases are inhibited. There must be 2 generators supplying the buses to provide a split DC bus configuration for Land 3 mode. Remember, all of the required equipment just listed must be in operation upon glide slope interception, and a missed approach must be initiated if any item fails prior to reaching the alert height. In addition to the foregoing, it is Eastern Airlines policy to use medium auto brakes on all Category 3 approaches. The following is a typical Cat 3 approach and landing at Miami International Airport. In this situation, you are on radar vector to intercept the ILS course inbound, landing on runway 9 left. For localizer intercept, position 1 autopilot to command. Also, heading and altitude modes are engaged. The auto throttles are engaged in speed select mode with V3 plus 10 selected. Set the inbound front CRS in both course windows and ensure that the nav receivers are properly tuned. As the localizer is approached on the intercept heading, land mode is selected. The FPI should display a white command legend, green speed select, heading select, altitude hold, amber VL, GS and land arm, and white and land 2. It is important that the crew monitor the FPI. The HSI displays the relative position of the course bar and glide slope. The beam deviation light should be illuminated until localizer and glide slope capture. Verify that both radio altimeters are set to the alert height of 100 feet. The ADI command bars provide visual cues to monitor autopilot operation as the aircraft intercepts the localizer course. As the localizer bar moves to center, a green VL light replaces the amber VL, indicating capture, and the heading select light goes out. The altitude hold green light stays on until glide slope capture. The captain calls a localizer capture and selects the localizer heading in the heading select window. The ADI command bars continue to provide visual cues to monitor the autopilot as the aircraft tracks inbound on the localizer. V3 is now set in the speed select window. At 2 dots glide slope, the gear is extended and final check accomplished. At 1 dot, flaps are extended to 25 degrees and the ground spoilers are armed. Auto brakes are armed. At glide slope capture, the amber glide slope light goes out and the green glide slope light illuminates. The altitude hold green light goes out, the captain calls glide slope capture, and speed select is adjusted to V approach and wind correction. The second autopilot is now engaged, and the autoland lights are tested. Land 3 light illuminates in the FPI, and the captain announces this verbally. The missed approach altitude is set in the window. The captain calls the altitude above field level upon crossing the outer marker. He also calls out altitude at 1,000 feet and 700 feet. At 700 feet, land arm turns green and the second autopilot is activated automatically and VL and GS green lights disappear. The second officer calls out altitude 100 feet above the ground. The amber DH lights on the radio altimeter and ADIs will illuminate, signifying alert height. At 100 feet in land 3 capability is frozen and will not drop back to a lower capability if a failure occurs. The second officer calls out 50 feet radio altitude. The captain says flare light when the light illuminates in the FPI. The autopilot initiates a flare. At 30 feet RA, the yaw command pointer in the ADI appears and decrab is initiated. Second officer calls off 30 feet radio altitude. The second officer calls out 20 feet. The ATS will control thrust to idle. At 15 feet, the beam deviation lights are inhibited. The second officer will call out 10 feet radio altitude. At touchdown, the captain calls rollout when the light illuminates in the FPI. Flare disappears from the FPIs. Speed select mode disengages and speed select disappears. The command bars in both ADIs go out of view. The yaw command pointer remains. The autopilot lowers the nose and controls yaw to track the runway center line. As the power is reduced to 31% N1, the ATS disarms and throttle off lights flash on the FPI. They may be extinguished by pressing either ATS disconnect button. The autopilots may remain engaged to provide rollout guidance down to 60 knots. When the autopilots are disengaged, land 3 and command disappear. Autopilot off lights flash along with the cavalry charge audio warning signal for 3 seconds. The light and audio can be canceled by pressing the autopilot disconnect button a second time. That was a simulated Cat 3 approach. Now let's discuss some additional information. The beam deviation lights are armed only when approach 2, land 2, or land 3 modes are engaged. They illuminate to warn if excessive localizer or glide slope deviation or receiver failures. With land 2 or 3 engaged and radio altitude below 200 feet, the auto land red light is armed and will illuminate for any one of the following conditions. The autopilot off light or beam deviation light illuminating, or touchdown is delayed more than 13.5 seconds after passing through 50 feet radio altitude. The Autoland lights are tested after the glide slope is captured by pressing either Autoland light. The Autoland lights flash and the beam deviation lights illuminate steadily. Failure of any system that was required to initiate the approach, either airborne or ground equipment, makes it mandatory that the approach be discontinued and a missed approach initiated. Furthermore, a missed approach will also be initiated if the pilot determines that an automatic landing cannot be safely accomplished within the touchdown zone. The go-around mode is an autopilot mode only. If a missed approach is initiated with autopilots off, the flight directors disengage and the ADI pitch bar commands are supplied by SRS. With the flaps extended and at least one autopilot in command, activating either go lever engages the go-around mode. This is indicated by the appearance of go-around on both FPIs. If both autopilots were engaged in land mode and go-around is engaged above 700 feet radio altitude, the second autopilot selected will disengage. If the radio altitude were less than 700 feet, the second autopilot remains engaged during the go-around. With the ATS armed, action on the go lever selects N1 mode for the auto throttles. The autopilots and throttles will provide a go-around N1 and adjust pitch attitude to fly an optimum go-around maneuver. The go-around mode can be canceled by disengaging the autopilots, pressing any upper mode, action on either electric trim switch, or by automatic disengagement because of an autopilot flight director equipment failure. Loss of land 3 capability prior to reaching alert height requires a missed approach. If one of the automatic systems fails below the alert height, the flare, touchdown, and landing may be completed using the remaining automatic system. All captains and first officers must receive ground training in the operational characteristics, capabilities, and limitations of required ground facilities and airborne systems. Flight training for the captain normally will be accomplished in the visual simulator. He must successfully demonstrate 2 ILS approaches using the automatic landing system, 1 missed approach from a low altitude, and 1 automatic landing also will be demonstrated. The first officer will observe an automatic landing performed by the captain while occupying his normal position and performing his assigned duties. This information is found in the A300 Flight Manual, Training Section 2.